This is John Whitaker for the Mathematical Analysis class, and this is our 21st video lecture. And last time we ended in the midst of a theorem that had two parts, and we proved the first part. I'd like to write up that theorem and prove the second part. So the theorem we were looking at said, part A, it said, if P sub n is a sequence in a compact metric space, X, then some subsequence of P sub n converges to a point of S. Part B, every bounded sequence in RK contains a convergent subsequence. Okay. So that's what we are. That was the theorem we were working on. And for the proof, we had done part A. So we're on to part B. And so what we want to do is prove that every bounded sequence in RK contains a convergent subsequence. Okay. So let P sub n be a bounded sequence. In RK. We're going to use a technique that we had used previously and approved, having to do with RK before. And that is, we're going to form a particular K cell and work with it. And that's going to contain this bounded sequence. So, since P sub n is bounded, then there exists a Q, and the P sub n, let me write them down because we're talking about RK, as I borrowed them. There exists a Q element of RK, and an M is a real number that's greater than 0, okay, such that, for the boundedness, the norm of P sub n minus Q will be less than M, be less than or equal to M, and that's for all n element of J. So that's a statement that's true for each term of the sequence. Now, let's get a representation for P sub n. So consider P sub n in general to be equal to alpha sub 1 comma n, alpha sub 2 comma n, all the way up to alpha sub k comma n. And Q, let's represent it by alpha sub 1, alpha sub 2, all the way up to alpha sub k. Okay. All right. Then, this norm of Pn minus Q being less than M implies that the sum, let me write it over here, So I'm going to compute that norm. So it implies that the sum, as maybe I runs from j, runs from 1 to k, of the alpha sub j comma n minus alpha sub j, that squared, you take 1/2 of that, and that would be less than m, and that is true for all n element of j. Okay. Thus, for all n element of j, and for each for each little j, I should say, in the set 1 to k, we have that the square root of alpha sub j comma n minus alpha sub j, that quantity squared, square root of that, that's got to be less than m. Okay. So this sum right here consists of k terms. And so if you just look at one of the terms, its form, okay, it's going to be less than the sum of all of those terms. So that's why we'll get this result. So, for all n element of j, this is the absolute value of alpha sub j comma n minus alpha sub j. Okay. That will be less than m. That's the absolute value. And that's true for each j element of the set 1 to up to k. Okay. So what this tells us, for all n element of j, what we do is we have that the minus m is less than alpha sub j comma n minus alpha sub j is less than m. And again, for each j in this set. And then we're going to subtract alpha sub j from both sides. We're going to add alpha sub j to both sides. So, for all n that are natural numbers, we have minus m plus alpha sub j is less than, if you want, you can say less than or equal to, alpha sub j comma n, which is less than or equal to m plus alpha sub j. And that's for j in 1 up to k. And this restriction, the minus m plus alpha sub j up to the positive m plus alpha sub j for each j, what that does is that forms a k-cell. Okay. So what we get is that the sequence p sub n, okay, is a subset of some I, where I is a k-cell. Okay. And what we've shown is that since each k-cell is compact, P sub n is a is a sequence in a compact set we're saying I. And what we do is we consider I along with the norm as a metric space. And so by part A of this theorem, what we have is that there exists a subsequence subsequence of P sub n, okay, say P sub n sub I, that converges to a point in I. And if it converges to a point in I, that means that the subsequence converges in RK, in the bigger space. And so that is the proof. I'd like to look at another theorem, and here's what it says. It says the subsequential limit points of a sequence P sub n in a metric space X form a closed subset of X. Okay, so remember the subsequential limit points are points in X such that there's a subsequence of P sub n that converges to it. And we're saying, if you take a look at that collection of points, that forms a closed set. Okay, so here's the proof. We're going to let E star symbolize or be the set of all subsequential limit points. Of P sub n. What we want to do is show E star is closed. So I'm going to look at some cases. So here's case one. It can be the case that there are no subsequential limit points of P sub n. Okay? That the sequence doesn't have any subsequence that converge. So here, case 1, as I've written, is that E star is equal to the empty set. Then, E star complement equals to X itself. Now, let little x be a point in big X. Note that the neighborhood of radius 1 about X, okay, is contained in X. What does this consist of? It consists of all the points P, if you will, whose distance from X is less than 1. And it's all the points P in X. So this neighborhood is a subset of our whole space. And so that means that X, little x, is an interior point. Big X. So every point, since that little x was just arbitrary, what we just showed was every point of the space X is an interior point. So that means X is open. Okay, with X being open, therefore, its complement is closed. And its complement is the empty set, which in this case is the same thing as E star, is closed. So we've proven the statement in this simple case. Okay. Case 2 is we're going to suppose that the subsequential limit points of P sub n is non-empty. Okay. So we're going to let Q be a limit point of E star. Now, the goal here is to show that E star is closed, okay? So how do we show that E star is closed? It's got to contain all of its limit points. So let's let Q be a limit point of E. We want to show Q is an element of E star. Okay? Now, I'm going to look at some subcases using this case. Subcase 1. Suppose that P sub n equals to Q. So the terms of the sequencer Q are all in element of J. Then Q is the only subsequential limit point It's not only the only, but it is, let's just say that it is a subsequential limit point. Because P sub n is a constant sequence. Converges to that constant. And if Q is a subsequential limit point, that means that Q is an E, or E star, I should say. So that handles this subcase. Subcase 2 really is that not every term of the sequence is equal to q. So the way I'm going to write that is that suppose there exists an n sub 1 that's a natural number such that p sub n sub 1 is different from q. What I'm going to be able to define next is a number delta, so it's a real number, that is the distance between q and p sub n sub 1. That's delta. Now, since q is a limit point, of E star, okay, that means there exists xi, element of E star, such that the distance between xi and q will be less than this delta that we had defined earlier over 2I. And that's, I'm going to say that for all I bigger than or equal to 2. That's natural numbers. Bigger than or equal to 2. Okay, the reason this is the case is Q is a limit point of E. What that means is that every neighborhood intersects, every neighborhood of Q intersects E star at some Q point. So I'm giving this this point x sub I, and my neighborhoods are being defined by this delta over 2 sub I, 2 to raise to the I, I should say. That's the radius of our neighborhood of Q. Okay, so these guys are non-empty, and that's how we get the x sub I's. Okay. Now, what we'll do is we'll say since, so we start making these observations, x sub 2 is an element of E star, then there exists an n sub 2 bigger than n sub 1, such that the distance between p sub n sub 2 and x sub 2 is less than this delta over 2 squared. Okay, so x sub 2 is an element of E star. What does that mean? That means that it is a subsequential limit point of the p sub n's. So that means that it's got to be some term of the p sub n's, some term that eventually gets really close to x sub 2, gets within any distance I want to give you of x sub 2, and so this is the distance that I'm giving you. So there's some terms of the p sub n that has to be that. I'm calling it p sub n sub 2. We're going to continue this line of thinking, where I'm going to work with x sub 3 next. So similarly, since x sub 3 is an element of E star, then there's going to exist some number, n sub 3, a natural number, bigger than n sub 2, such that the distance from p sub n sub 3 to x sub 3 will be less than delta over 2 raised to the third. What we do is we continue this process to form a sequence, to form a subsequence. Okay. Form a subsequence. P sub n sub I of P sub n such that for all i's bigger than or equal to 2, the distance between p sub n sub I and q will be less than or equal to, by the definition of the metric, the distance between p sub n sub I and x sub I plus the distance between x sub I and q. But this is going to be less than, this distance we just said was going to be delta, if we continue this process, it's going to be delta over 2 to the I plus, this is going to be also delta over 2 to the I, which is equal to, well, it's the same thing, two of them, so it's equal to delta over 2 to the I minus 1. Okay. So, for every I that's a natural number, here's what we have. The distance between p sub n sub I and q will be less than or equal to delta over 2 I minus 1. So when I was equal to 1, what happens is that you just get delta on this side, and that distance is delta, so that's what we have to equal to. So here we're going to let epsilon be greater than 0 be given. We choose I large enough and this can be done because of the natural numbers are not bounded above, such that delta over 2 to the I minus 1 is less than epsilon. And so for all I greater than or equal to big I, the distance between p sub n sub I and q will be less than this delta over 2 to little I minus 1, which is less than or equal to delta over 2 to the big I minus 1, which is less than epsilon. So this natural number, such that if you go beyond that natural number in this subsequence, p sub ni, their distance from q is less than the epsilon was given to me. That says that the subsequence converges to q. So we formed a subsequence of the p sub n's, that's p sub n sub I, that converges to q. What that means is q is a subsequential limit point of p sub n. So that means q is an element of E star. But that's what we wanted to show because q was a limit point of E star. So, so that means that E star is closed. And it was closed in all possible cases. And that's the proof. Okay, next I want to talk about a particular type of category, if you will, of sequence. And that's something called a Cauchy sequence. So here's the definition, what it means to be a Cauchy sequence. A sequence p sub n is said to be I should say, let me back up. A sequence piece of n in a metric space S is said to be Cauchy or a Cauchy sequence. Let's write that down. A Cauchy sequence if for each epsilon greater than 0 there exists I guess I call it a big N element of J, such that for all little n and little m bigger than or equal to big N, the distance between p sub n and p sub m will be less than epsilon. The idea is that in Cauchy sequences, the terms of the sequence can be made arbitrarily close to each other. By going far enough into the sequence. In the sequence. Okay. So I'm going to repeat this. Essentially what we're saying to be Cauchy is that no matter what distance you give me, we're calling that epsilon, there is a spot in the sequence, we're calling that big N, such that from that spot on, anytime you take any terms of the sequence from that spot on, their distance from each other is less than the distance you gave me, the epsilon you gave me. And the distance you have, the spot in the sequence that you have to go to make this happen for a Cauchy sequence depends on the epsilon that's given to you. Well, let's look at an example. So we'll look in R with the usual metric. So as an example, the sequence 1 over n is a Cauchy sequence. And the proof of that is the following. We let epsilon be greater than 0 be given. What I'm looking for is an n that's a natural number, such that for all n and m bigger than or equal to this big N, the distance here is the difference inside absolute values, of 1 over n minus 1 over m will be less than epsilon. Okay? So this is the distance between the x of n and x of m terms. Okay, so we want 1 over n minus 1 over m to be less than epsilon. So here's what we do. We note that the 1 over n minus 1 over n in absolute values is going to be equal to 1 over n plus or minus 1 over m, which will be less than or equal to, by a fact that we're proving about that absolute value of complex numbers. It's going to be 1 over n inside absolute values plus absolute value minus 1 over m. and that's equal to 1 over n plus 1 over n. Now, since 1 over n we've proven converges to 0, then there exists a big N element of the natural numbers such that for all n bigger than or equal to this big N, the absolute value of 1 over n minus 0, which will be equal to just 1 over n, will be less than whatever positive number was given to me. And I'm going to say we were given epsilon over 2. So for all n and m bigger than or equal to big N, the absolute value of 1 over n minus 1 over m, which we've shown to be equal to 1 over m plus 1 over m, will be less than epsilon of 2 plus epsilon of 2, which equals to epsilon. Okay, so for all n and m bigger than or equal to n, this 1 over n minus 1 over m is going to be less than epsilon. Thus, 1 over n is Cauchy. Now, here's another example. The sequence in R that's always n, that's just a set of natural numbers. However, it's not Cauchy. And I'm not going to go through the details. Instead, I'm just going to say this comment. This sequence is not Cauchy because, remember, what Cauchy means is that after some point in the sequence, the terms from that point on are arbitrarily close to each other. Well, these terms from any point on have terms after them that will be separated by any number you want. Okay? So if I go to whatever, the nth term here, I can find later two terms that are separated by 10. Okay? And so they're not within some epsilon units that's less than 10 of each other. Okay. Kind of a useful definition that we'll have next is that about the diameter set. So definition, let E be a non-empty subset of a metric space X, and let S be the set of real numbers of the form the distance from P to Q with P being an element of E and Q being an element of E. Then the sup of E is called the diameter of E. Now, we'd say the sup exists is provided the set S is bounded. Okay, bounded above. And so here, in terms of the sup existing as a real number, but for example, let me look at the first example here. Let's let E be equal to the set that goes from 2 to 7, which is subset of R. Then the diameter of E, okay, which I'll symbolize as DIAM of E, it's going to be the sup of the distances that will happen here, and that's going to be 5. another example. If we let E be equal to 1 to infinity, then we could say that the diameter of E does not exist because the sup of all the distances between the points in this set would be doesn't exist. Okay? Or you could say that the diameter of E is equal to infinity. So it doesn't exist as a number, but we could say it's infinite. Okay? Well, let me write down, at least prove half, of a theorem that has two parts. So if E bar is the closure of a set E in a metric space X, then the diameter of E is going to be the same thing as the diameter of E closure. Part B is part A. Part B, if Kn is a sequence of compact sets in X such that the case of n contains the case of n plus 1 and case of n is not equal to the empty set. And if the limit as n goes to infinity of the diameter of the case of n equals to 0, then the intersection as n runs from 1 to infinity of the case of n's consists of exactly one point. Okay, so these are two facts having to do with diameters of all kinds. Okay, so the proof, part A, okay, so we're trying to show that the diameters of E and E closure are the same. So here's the first thing there. Since E is a subset of E closure, remember what E closure is. E closure is E union all of its limit points. Then S sub E, if you will, right down here, which I'll label as a set that consists of all the real numbers that are distances between P's and Q's, such that P and Q are elements of E. That set is a subset of the set of all real numbers that are distances between, let's say, P's and Q's, such that P and Q are elements of E closure, okay, which I'll call S of E closure. Okay. So the sup of E must be less than or equal to the sup of E closure. And so that tells us that the diameter of E must be less than or equal to the diameter of the closure. So the way we're going to try to prove that these diameters are the same is we're going to show, hey, one of them is less than the other, and then we're going to show that the other is less than the first. So right now I have the diameter of E is less than the diameter of E closure. We need to show the reverse, that the diameter of E closure is less than or equal to the diameter of E. Therefore, they must be the same. That's what we're working on. Okay, so here's what we'll do. We'll fix some epsilon greater than 0 and choose P an element of E closure and Q an element of E closure. Then what we have is that P would be an element of E union the limit points of E, and Q is an element of the same thing, E union the limit points of E. We will consider several cases. Following cases. So the cases are based on where P and Q can be. Okay, so case 1. Okay. If P is an element of E and Q is an element of E, then there exists P prime, an element of P, P prime is EP, and a Q prime element of E, Q prime will be equal to Q, okay, such that the distance between P and P prime is less than epsilon, and the distance between Q and Q prime is less than epsilon. In case 2 is going to be, not that both of them are at E, but if exactly one of P or Q is in E. So both of them were in there. Exactly one was in there. Doesn't matter which one. And in the other cases, neither of them were there. So for case 2, without loss of generality, low log, without loss of generality, say P is an element of E. And we know that Q is an element of P prime. Okay, then there exists a P prime element of E, namely E equals P prime, okay, and a Q element of E prime, such that the distance from P to P prime is less than epsilon, and the distance between Q and Q prime is less than epsilon. Case 3, neither P nor Q are in E. Well, they were in E closure, so that means that both P and Q are in the limit points of E. So, the distance between, well, what this means is, then there exists P prime element of E and Q prime element of E, such that the distance between P and P prime will be less than epsilon, and the distance between Q and Q prime will be less than epsilon. I made a mistake in something I wrote earlier. I'm going to correct it. I know we're out of time, essentially, but I'm going to correct this. Here, in this case, too, I said, okay, then there exists a Q and element of B prime. I shouldn't have said that. I should have said Q element of B. Then there exists a Q prime element of B. That's what I should have said. I made a mistake there. Such that the distance between Q and Q prime is less than epsilon. Okay, well, what does it mean? Why is that true? What does it mean for Q to be an E prime? It's a limit point. What does it mean to be a limit point? It means every neighborhood of Q intersects E at some non-Q point. And so, what I'm thinking of is if you let the neighborhood about Q that we consider to be the neighborhood of radius epsilon, there's got to be some point in E, which I'm calling Q prime, that's in that neighborhood. And so the distance between Q and Q prime has to be less than epsilon. So I made a mistake there in my notation. And here, we're using that same idea. Okay? Because P and Q are both limit points, there's points in E and 2 points in E. One that gets it can be made to be really close to P, and one that can be made really close to Q, because P and Q are limit points. Okay. So here, what we say is, so in all cases, there exists P prime and Q prime in E. Okay? Such that the distance from P to P prime is less than epsilon, and the distance